20th International Physics Olympiad. Year 1989. IPHO. I offer private tutoring for preparation for physics Olympiads. I currently have openings. Write to me if you are interested. There is a discount for group lessons. My email is fred1996@hotmail.com. Problem 1. Boiling liquids. The solution to this problem can be found at the link in the description under this video. Consider two liquids A and B insoluble in each other. The pressures Pi, I equal A or B, of their saturated vapors obey, to a good approximation, the formula 1. Where P0 denotes the normal atmospheric pressure, T, the absolute temperature of the vapor, and alpha I and beta I equal A or B, certain constants depending on the liquid. The symbol ln denotes the natural logarithm, that is logarithm with base e equals 2.7182818. The values of the ratio Pi over P0 for the liquids A and B at the temperature 40 degrees Celsius and 90 degrees Celsius are given in Table 1.1. Question A. Determine the boiling temperatures of the liquids A and B under the pressure P0. Question B. The liquids A and B were poured into a vessel in which the layers shown in Figure 1.1 were formed. The surface of the liquid B has been covered with a thin layer of a non-volatile liquid C, which is insoluble in the liquids A and B and vice versa, thereby preventing any free evaporation from the upper surface of the liquid B. The ratio of molecular masses of the liquids A and B, in the gaseous phase, is gamma equal mu A over mu B equal 8. The masses of the liquids A and B were initially the same mass m, equal 100 gram. The heights of the layers of the liquids in the vessel and the densities of the liquids are small enough to make the assumption that the pressure in any point in the vessel is practically equal to the normal atmospheric pressure P0. The system of liquids in the vessel is slowly, but continuously, and uniformly, heated. It was established that the temperature T of the liquids changed with time tau as shown schematically in the figure 1.2. Determine the temperatures T1 and T2 corresponding to the horizontal parts of the diagram and the masses of the liquids A and B at the time tau 1. The temperatures should be rounded to the nearest degree in Celsius, and the masses of the liquids should be determined to 1/10 of gram. Remark: assume that the vapors of the liquids, to a good approximation. First, obey the Dalton law stating that the pressure of a mixture of gases is equal to the sum of the partial pressures of the gases forming the mixture and, second, can be treated as perfect gases up to the pressures corresponding to the saturated vapors. 20th International Physics Olympiad. Year 1989. IPHO. Problem 2. Rotating masses. 3 noncollinear points P1, P2, and P3, with known masses M1, M2, and M3, interact with one another through their mutual gravitational forces only. They are isolated in free space and do not interact with any other bodies. Let sigma denote the axis going through the center of mass of the three masses, and perpendicular to the triangle P1P to P3. What conditions should the angular velocities omega of the system, around the axis sigma, and the distances P1 P2 equals A, 1 2, P to P3 equals A, 2 3, P1 P3 equals A, 1 3, fulfilled to allow the shape and size of the triangle P1P to P3 unchanged during the motion of the system? That is, under what conditions does the system rotate around the axis sigma as a rigid body? 20th International Physics Olympiad. Year 1989. IPHO. Problem 3. Proton microscope. The problem concerns investigation of transforming the electron microscope with magnetic guiding of the electron beam, which is accelerated with the potential difference, U, equal 511 keV into a proton microscope, in which the proton beam is accelerated with the potential difference, U. For this purpose, solve the following two questions. Question A. An electron, after leaving a device, which accelerated it with the potential difference, U, falls into a region with an inhomogeneous field, B, generated with a system of stationary coils L1, L2, etc. till Ln. The known currents in the coils are I1, I2, etc. till In, respectively. What should the currents I1', 2', etc. till In' in the coils L1, L2, etc. till Ln be, in order to guide the proton, initially accelerated with the potential difference, U, along the same trajectory and in the same direction as that of the electron? Hint: the problem can be solved by finding a condition under which the equation describing the trajectory is the same in both cases. It may be helpful to use the relation 1. Question B. How many times would the resolving power of the above microscope increase or decrease if the electron beam were replaced with the proton beam? Assume that the resolving power of the microscope, that is the smallest distance between two-point objects whose circular images can be just separated, depends only on the wave properties of the particles. Assume that the velocities of the electrons and protons before their acceleration are zero, and that there is no interaction between own magnetic moment of either electrons or protons and the magnetic field. Assume also that the electromagnetic radiation emitted by the moving particles can be neglected. Note, very often physicists use 1 electron volt, and its derivatives such as 1 kilo electron volt or 1 mega electron volt, as a unit of energy. 1 electron volt is the energy gained by the electron that passed the potential difference equal to 1 volt. Perform the calculations assuming the following data. Rest energy of electron is 511 kilo electron volt. Rest energy of proton is 938 mega electron volt.